Hi, I'm Debbie with Nixing Publishing, and we are continuing our discussions about graphene with Adrian Nixon, our editor-in-chief of the Nixing Journal. And Adrian comes to us from Yorkshire, England. Hi, Adrian. How are you doing today?
Really good, Debbie. How are you?
I'm doing well, and I'm excited about what we're going to be talking about because it's something that we've never talked about before. And it's two words that don't seem to go together to me: graphene mirrors. And one's reflective and one's just black. So I'm wondering, how does this work out? How does graphene go with mirrors?
Yeah, it's good thinking that. This came about from my other day job, which is I'm a board member for the International Space Elevator Consortium, as you know. Yeah. And we made a video about that with Dennis a little while back.
Yeah.
Now, as part of that thinking, we're making a graphene tether. Is a piece of material that connects the surface of the Earth up to orbit, and it's made of graphene, layers of graphene. So individual layers all stuck together. And multi-layer graphene is, quite rightly, as you've pointed out, Debbie, graphite, which looks like the stuff in pencils. And there's nothing really remarkable or shiny about that. And as you well know, Debbie, graphene powders, they sort of look, well, black, don't they? This is the graphene made from biochar. And again, not too much remarkable about or mirror-like about a black powder. So why do I think it's going to be like a mirror? For that, I'm going to have to share my screen. So you remember this, Debbie, with what graphene looks like?
Van der Waals that make the electrons moving above and below the graphene?
Yes, the Van der Waals forces hold the graphene layers together to make graphite. And in this case, what we're interested in is something slightly different, which are these pi orbitals, which are, as you quite rightly pointed out, the electrons of the fourth bond of graphene. Each one of those graphene carbon atoms here has a little bit of a contribution towards this cloud of electrons above and below the plane of the ring. So we have this sea of electrons, which goes over the whole surface of the molecule. The reason that's important is because this sea of electrons is very similar to the sea of electrons we get in metals. So even though this is carbon, we can predict from just looking at this structure here that this is going to look slightly metallic as the light bounces off this electron cloud above and below the plane of the graphene layer.
Is it because it's a sheet? Because I know when you look at the graphite itself, you can tell it does have a sheen to it.
Yeah, let's look at a lump of graphite. So you'll remember that we originally saw this piece of graphite at the NGI, the National Graphene Institute, and now it's at the GEIC. This was given to the GEIC by First Graphene, and they're an Australian company that are also based in Manchester as well. And they've got a source of very, very high quality Sri Lankan flake graphite. You can see, I think, does that look a little bit metallic to you, Debbie?
It does to me. I mean, I can see that there's a sheen to it, if you notice where the light's hitting it.
And that's what got me thinking, because the reason that looks metallic and this doesn't, they're the same material, they're both graphite, is it's a combination of the Sri Lankan graphite has very big flakes. They're still fairly small, but for our purposes, but they're much bigger than here. And if you remember, the graphite is like lots of decks of playing cards,
right,
all stuck together, where an individual card is the graphene, and then the deck of cards is graphite. Here, those decks of cards, if you like, are very, very small and all jumbled up. So they're scattering light in all sorts of different directions. But in this sample here that you're looking at on this slide, if you like, the decks of cards are much bigger. That's what the flake size means. And they're more ordered as well. So now, because they're getting more ordered and more coherent, it's scattering the light in a more coherent way, and we're beginning to see more of the metallic characteristics coming out.
I wouldn't have expected that
until I saw this lump of rock.
So you could, it's almost like you could put it all down into one single layer and then it becomes reflective?
There you're onto something, right? So now if we take this idea about the bigger the flakes are and the more ordered they are, the more they'll scatter light in a more of a metallic way, and they'll start looking more and more and more metallic, more and more shiny. Coming back to the space elevator tether, we're going to have very, very big sheets of graphene, and they're going to be very, very ordered, laid on top of one another. And it's not really going to be graphite as we know it. So let's call it Nixene for the sake of argument for the moment. So sure. Just to separate out in your mind, this is not graphite we're looking at, this is a brand new material. And then what the consequences of thinking about that, what would that look like? It would look even more metallic, even more shinier, and eventually we'd end up with a perfect silver mirror.
Oh my gosh, because of the layers.
Exactly. And because they're very, very big layers and they're incredibly well ordered. So you can see at the top right of the screen here that we've got a little graphic showing you all those individual layers now very, very highly ordered. And that circle in the middle is a representation of what the graphene would actually look like when it's multi-layered. So we got multi-layered CVD graphene. It could be polycrystalline, it could be single crystal. Single crystal would be the ideal, but polycrystalline would probably do this, and it would look like a perfect silver mirror.
Wow, so they could do that with the polycrystalline there's only a few places in the world that are actually making it.
Very good point, Debbie, because now we're beginning to see industrial manufacture of graphene, CVD graphene, at fantastic scale. So we're now getting tens of thousands of square meters of graphene being able to be produced on copper foils and then separated off. It's only a matter of time before people start layering this up and discovering what the bulk material actually looks like, that we reckon, let's make a wild prediction. We'll say when they start layering it up, they'll find they can make perfect mirrors. And these mirrors would have some really interesting physical properties. Can you think of any uses for this, Debbie?
If you're going to do a perfect mirror, then first thing I think of is the big mirrored dishes, like a satellite type of a dish or something like that.
Yeah, maybe for telescopes or reflective shields, space applications, that sort of thing. Maybe the gravitational wave observatories up in space, they need very, very good lightweight mirrors. And these will be thermally stable, chemically stable, extremely hard, extremely tough and robust materials. They're unlikely to be ductile, so you can't draw them into wires, so they're not going to be stretchy either. So they're going to have a range of really amazing properties.
Incredible. I mean, to think that you could, it's like we keep adding all these different things about graphene every day. You know, you can't say that a single layer of graphene is going to be, you know, a mirror, but you can say that you very likely could stack up a whole bunch of them and add that to the list of all the superlatives that graphene has.
Yeah, and interestingly, as we speak, nobody's made this. This is just purely and simply theoretical at the moment, coming out from our own work. Yeah, we'll find out if this is actually capable of being done.
So this is kind of an interesting video for all of our viewers, because typically we're doing analysis of stuff that's already been done. And this is conjecture based upon scientific analysis of what could be.
Yeah, and there's one final thing. The university, is it Massachusetts Institute of Technology, Lowell University, they've made something, a new form of carbon that they call eucarbon, which you may have heard of, Debbie.
Yeah, I heard something about that.
Not many people have heard of it. It's only because we're working in this field. It doesn't come up on the graphene searches because it's not graphene, but they've found that when they use like a CVD method of making this carbon, they've laid down what seems to be a mix of maybe multi-layer polycrystalline graphene and maybe diamond-like carbon. But the interesting thing is, it's turned out to be mirror-like.
Oh, for heaven's sakes. Carbon is so versatile. It's incredible. It really is.
So we may see graphene mirrors coming sooner rather than later.
So, and because graphene's so tough, then you would basically have an unbreakable mirror?
Yeah.
You can forget all those years of bad luck for breaking a mirror.
It would never break.
So now, what would your timeline be if you were to take a guess at how long before somebody, you know, creates something like this with layering up?
Yeah, that's a good question. Well, we know that graphene can already be made at scale industrially fast. So we know a meter per minute, isn't it? This current speed that graphene can be made. We know it can be made on large scale. So the machines exist, the production exists. So I would say probably give it within 2 years, we'll probably be seeing that. And it might happen sooner rather than later. In fact, it may even happen that somebody's made it already and they're keeping it in secret. We'll find out.
Adrian, thanks for your time, and we'll see you next time.
Pleasure, Debbie. Bye-bye.